Okay, we have discussed the basics of PN junction and also began our discussion on the transistors, bipolar junction transistor. Today, we will continue from there on with the discussion on the BJT, MOSFET characteristics, metal oxide semiconductor field effect, and then little bit of op amps also. Because we have few sessions on these topics like op amps etc. to come up later on. So, today we will discuss BJT, MOSFET and then bit of CMOS, amplifiers and op amp concepts, and we will see how far we can go with the basic op amp circuits. We can continue in subsequent lectures on these topics. Yesterday we discussed the forward bias PN junction, which will inject plus charges holes, plus charges we call it as holes into N region, and some amount of electrons also will injected, but number of electrons injected from right to left will be small compared to number of holes injected, because this is very heavily doped. P plus means heavily doped, about 10 to the power 20 per centimeter cube dopants. Here it may be about 10 to the power 15 or 16 per centimeter cubed. Okay. This is a reverse bias diode, where current flow is very small, and the current flow is due to some of the minority holes which are present here rolling down the potential hill. Then what we said is, if I merge these two together, forward biased PN junction injects holes, and if this junction, reverse biased junction, is kept very close to that, maybe a couple of microns, these holes injected can be collected by this, because there is a potential downhill. So, there will be current flow from this side to this side. So, what we said is, we have done this. So, this is the bipolar junction transistor. You call it bipolar because if you take a junction, there is hole injection from P plus to N, large quantity, small quantities of electron injection from N to P. So, both holes and electrons participate in the transistor action. That is why it is called bipolar junction transistor. Now, what we said then is, we have discussed this PNP transistor, PNP transistor. This is the emitter which emits the holes, this is the collector which collects the holes, this is the base region. Okay. N is the base. So, emitter, base, collector, forward biased emitter base junction, reverse biased collector base junction, PNP transistor. So, you can see out of the total current injected into the emitter contact, part of it is, or most of it is whole current IP injected from the emitter to the base. Almost everything is collected because the distance is very small. So, IPC is almost equal to IP, IP is almost equal to I. Therefore, IPC is almost equal to I, and you can say that IPC is alpha times I. Alpha is very close to 1, but definitely less than 1. Then, so that is one current is due to the transfer of carriers from this region through this base to the collector. Otherwise, if this were not there, that would have been flowing through this loop. Now, you have transferred this current from this input loop to the other loop. Okay. And a forward biased junction has a very low resistance, and reverse biased junction has high resistance. So, you transfer the charges from a low resistance loop to high resistance loop. That is why it is called transfer resistor or transistor. So, if you see the collector current component, one is due to what is injected from emitter and reaching the collector. Other one, even if this emitter is not biased, only the PN junction is present, there is that I naught flowing through like this, reverse saturation current, which actually is negligible compared to this IPC. So, IC will be whole current reaching the collector plus reverse saturation current, and whole current reaching the collector is alpha times IE, where alpha is very close to 1, and you get the collector current as alpha times IE plus IC naught. So, alpha is called the current gain in the common base mode. See, base is common to both input and output. So, in that mode it is called common base current gain, which is less than 1. You will see then what is the use. When you use it as a voltage amplifier, you will get voltage gain. Okay. So, now the base current in the transistor, bipolar junction transistor, BJT is emitter current minus collector current, that is out of the total emitter current, part of it is diverted to this in the form of recombination current. Okay. So, that is IB is therefore IE minus IC. Now, IE from here first equation I can see is IC minus I naught divided by alpha is that IE and minus IC is here. I can simplify it, it turns out to be IC into 1 minus alpha by alpha minus this. Calling 1 minus alpha by alpha as beta, you get IC beta times IB plus beta plus 1 times IC naught. Beta is actually the current gain, collector current divided by the base current. So, here I take this current by divided by the base current, that is the current gain in the common emitter configuration. If I use this as input, make that as a common terminal. So, beta is collector current by base current, neglecting of course, this will be very small, it is the reverse saturation current part of it. So, beta is alpha by 1 minus alpha, where alpha is let us say 0.99, this will be 1 minus 0.99, that will be 99. 0.99 divided by 0.01, that is 99. Okay. Now, that is the PNP transistor. Note the polarities, emitter is plus, base is minus here, forward bias, collector is reverse biased, collector is negative and this is positive. Now, you just can have also instead of PNP transistor N plus PN transistor, NPN transistor. The symbol for PNP transistor is shown at the corner here. You can see the emitter E, arrow pointing towards this, injecting that current flow is in that direction. Current flow is from emitter to the base and then the collector, emitter, base, collector. Now, NPN transistor, everything will be reversed, current flow will be opposite, both polarities will be reversed. So, this is NPN transistor. Okay. You can see compared to the PNP transistor, this is negative, this is positive. The concept remains the same thing, emitter based junction is forward biased, collector based junction is reverse biased. So, N is positive. So, now here electrons are the ones which are injected from the emitter and reaching the collector. So, electron flow is in that direction, okay, but the current flow will be exactly opposite. See, when a plus charge moves in the x direction, plus x direction, current flow is plus x direction, because charges move in the direction of current flow. But now, electrons have a negative charge, therefore, if the electrons are moving from in the plus x direction left to right, the current flow is in the opposite direction because of negative charge. So, I have marked the actual current flow direction as INE, which actually is due to the injection of electrons from emitter to the base. So, all that you have to know is that if charges are injected in that direction, current flow is in the opposite direction. Okay. So, here same concept, except all the polarities are reversed, current flow are reversed, the symbols is reversed. Emitter, base, collector, current flow is entering, coming out of the emitter like that. So, arrow is in that direction, okay, and current flow is from collector to the emitter, collector to the emitter like this. But the equations do not change. IC is current flow is alpha times I plus IC naught. You can see that IC naught is the same direction as this INC. Just like in the previous case, IC naught was in the same direction as IPC. So, these two add up. These two add up, you get alpha times I plus IC naught as IC. In terms of beta, beta is IC by IB, you get IC is beta times IB plus beta plus 1 IC naught. Please note that the voltage polarities and the current flow directions in NPN transistors are exactly opposite to the PNP transistor. Okay. So, symbol is like this. We will come back how this can be used as an amplifier little later. Okay. Now, the collector current is alpha times I. So, if I bias it like this, I apply forward bias to the emitter, I talk of PNP because easy to see the direction of current and charge flow direction, I E is related to I C by this constant alpha, which is very close to 1. So, you can see here, if I keep I E constant and vary V C 0 to positive value, that is the reverse bias, whatever holes are injected from here are reaching this point are collected, because the potential barrier here is for the holes that is sloping down. So, whether it is 0.6 volts or 0.8 volts or 1 volt forward the slope, it does not matter. All the holes reaching this end will be collected. That is why once you fix the emitter current, collector current will be practically constant. But so you can see 1 milliampere is IE, IC also will be very close to 1, 0.99 maybe. 2 milliampere is IE, but throughout it will remain 2 into alpha, that is 0.99 into 2. Okay. But if I reverse this polarity, what happens? If I make this plus and this minus, you are forward biasing this p-n junction, which will actually inject holes from the right hand side to the left hand side. So, here you are injecting holes from the emitter to the collector, okay, but you are holding this current constant. So, whatever holes pumped back will flow back to the base, but across the junction the current will be due to injection of charges from emitter to collector minus injection of charges from the collector to the base, that will keep on increasing. So, if I keep emitter current 1 milliampere, if I forward bias the collector base junction, the current will fall, it can even become 0. And this voltage here range will be just about 0.6 volts or so, not more than that, the entire range what I have marked here. So, this region here where the collector current changes proportional to the emitter current is called the active region. You would like to use that when you use it as an amplifier, and this region, green region here what I have marked, IE is 0, only the reverse saturation current, that is the cutoff region. Okay. There is no input current to this, that is the cutoff region, this is the active region, and this region is called the saturation region, where both emitter base junction and collector base junction are forward biased. So, in this region what happens is the current in the collector here does not change proportional to the change in the current emitter current. You may change 1 to 2 milliampere, but you can see at this voltage the current does not go become 1, does not become 2, it is much smaller than that. So, that is why it looks as if the current here is saturated, that is called saturation region. That is, the collector current will not be faithful reproduction of the emitter current. So, you will not be able to use it as an amplifier. So, amplifier is this portion. Okay. This is the common base configuration. Common emitter configuration, what you have done is, you can see same thing, but here the input is here, but in this case the input is here. You keep the emitter base junction VB forward bias, collector base junction you vary from 0 to large value. Okay. When the voltage is large, for example, let us take this as 0.6 volts emitter base voltage. If this voltage also is 0.6 volts, VC is 0.6 volts, this is 0.6 already, this voltage is 0. If I make this larger than 0.6 volts, this voltage will be reverse bias, plus, okay, minus plus. So, when it is reverse biased, collector current will be proportional to the emitter current and therefore, proportional to base current by this relationship beta times IB. Beta is large. If it is microampere, you will have milliampere current there. Now, okay, if this is 0.6 volts, if this is 0.6, I said this will be 0 here, because 0.6 has gone into this. If this is less than 0.6 volts, if the p-n junction is forward biased 0.6 volts, this will voltage, since this is 0.5, plus minus minus plus, so that this is 0.5. Okay. So, as a result, if this voltage is less than this p-n junction voltage 0.6 volts, there will be a forward bias voltage across that. That will be a situation where emitter base junction and collector base junction both are forward biased. At that point, as we saw here, when both the junctions are forward biased, collector current starts falling. Same thing happens here. Beyond this line, the collector base junction is forward biased, therefore, the current collection is not proportional to the emitter current, it is not proportional to base current, so it falls down. So, this portion is the saturation region, this is the cutoff region, this is the active region. So, you use an amplifier in this region. Okay. Now, let us switch gears to another device, that is MOSFET. The structure of the MOSFET, I have shown the cross section, exact cross section. This is the p type substrate, these two are the n plus regions. I am talking of one type of channel transistor called n channel MOSFET. This is the source, this is the drain, because this can supply electrons. If it can flow through this region and reaches here, it can collect this region, or it can drain those electrons which are reaching here. So, source, drain, there are the two terminals, and the red color is the oxide here. Silicon, oxide, this gate can be metal or very heavily doped silicon. It looks like a metal. So, metal, oxide, semiconductor, this portion, that is why it is called MOS, metal oxide semiconductor. I can apply voltage to this metal. This is just a structure. I am showing what happens when you apply a bias. Supposing I do not apply any voltage to the gate, this is called the gate, with which I can control the current flow. Source, gate, drain. Gate is for controlling the current flow between the source and the drain. Okay, how it happens we will see soon. Now, I do not apply any voltage to the gate, VGS is 0. This is the source, that is 0. All that I do is connect this to ground, apply voltage between this point and this point. These two are shorted together. So, if I apply voltage between these two, make this plus. Notice that n region is made plus with respect to p, that means it is reverse biased. There will be only a reverse saturation current, very small current, ID is practically 0. It is strictly speaking, it will be reverse saturation current. Okay. Now, so it does not serve any purpose. All that is happening is reverse saturation current. So, even if VD is varied from 0 to 10 volts, nothing happens. Now, look at here. Here, what I have done is, I have applied a voltage between the gate and the substrate, and substrate is connected to that terminal there. You can say gate to source or gate to substrate. So, let us take a look at this. When I apply voltage between the two, it is like a metal insulator and another semiconductor, look at it as a metal. So, it is like a capacitor. So, when I apply voltage to this, plus charges are induced on the gate, minus charges are induced on the other side of the oxide, and these minus charges are electrons. So, when I apply plus voltage, electrons are induced due to the field lines from the gate to the channel, that is the field effect. When I apply voltage between the gate and the substrate, that field effect induces negative charges. It is like a parallel plate capacitor. Plus voltage if I apply, it gets plus charges here, and minus here on the right hand side, this one charges negatively, plus charge and negative charges in semiconductor are electrons. Okay. So, you have plus charges and minus charges. If I see it like that, okay, plus charge there, minus charge there, and those are electrons which you see here in the channel, plus charges and minus charges. So, the moment you have electrons here, right through the path, if I apply voltage between the drain and the source, there is a straight away there is a path between the source and drain. This is N, this is N, this is N. So, it is like a resistor. So, when I apply voltage, this begins to field is from this region to this region, so electrons will be attracted to the plus terminal. So, electrons will flow along this channel in this direction, which would mean current will flow in the opposite direction. Okay. So, you have a voltage drop across this is called the channel. Source, drain and the channel. Channel is the path created by this applied electric field, okay, and this path is created because of the negative charges, electrons. And so, there will be current flow from source, from drain to source, because of charge, net electron flow from source to the drain. You can look into it as, say I have shown source and drain a open switch. This is a open switch, there is no path. But the moment I apply voltage between the two, the moment the charges are created here, the switch is closed. But it is not an ideal switch, there is a resistance along this path. So, therefore, the current will not rise infinitely, the current will rise like this. As I increase the drain to source voltage, the current will increase linearly for a given gate voltage. If I increase the gate voltage from VGS1 to VGS2, more charges are there. More charges means less resistance, that means more current. So, I will have another characteristic like that. If I increase it to VGS3, more voltage, gate voltage, more charges, more will be the current for this thing. So, I get linear characteristic like that. So, this is the MOSFET action, metal oxide semiconductor transistor action. You can control the drain current by changing the gate voltage and the drain voltage. Okay. Now, let us see what happens if I keep on increasing the voltage. If I keep on increasing further, notice when the current flows from drain to source, because of charge flow in this direction, there is a voltage drop along this channel, and these electrons are not induced, sufficient electrons will not be created unless otherwise the gate voltage VGS is above a certain voltage called threshold voltage. This depends upon various parameters like the oxide thickness and the substrate characteristics. Okay. Thicker the voltage, thicker the oxide, more voltage you must apply to induce the required charge. Okay. So, what we are trying to say is a minimum voltage is required, which you call it as threshold voltage, to create these charges. Now, let us say you applied 2 volts here, and let us say minimum voltage required to create this charge is 1 volt. When the drain voltage is small, the voltage that is available for creating these charges is applied voltage minus that 1 volt. See, till 1 volt is appearing across the gate and this channel, not much charge is there. So, charge created is due to whatever difference is there between the minimum voltage threshold voltage and the applied voltage. So, again looking at the example, if applied voltage is 2 volts and if the minimum voltage is 1 volt, the charge that is present here is capacitance into Vg minus V threshold voltage. That is Vg is 2 volts, threshold voltage 1 volt. So, Vg minus V threshold is 1 volt, 1 volt into the capacitance, that is the charge that is induced here. The assumption is till you apply 1 voltage to the gate, the charge is negligible here. I am not getting down into more of that physics. Okay. Now, if I keep increasing this current go in that direction like that, the voltage drop from here to here increases. Okay. So, initially when this voltage drop was negligible, throughout a voltage of 1 volt was available between the gate and the channel to create the charge. But if there is a drop of half volt from here to here between the drain and the source, if there is half volt, the voltage that is available for creating this charge is applied voltage 2 volts. I require at least 1 volt to create the initial charge. So, the voltage available here is 1 volt. So, 1 volt into capacitance is the charge here. If the drop in this direction is 0.5 volts, okay, here 1 volt was available, out of that 0.5 voltage has gone in this direction. So, voltage that is available here is only 0.5 volts. That means, the charge in this portion now will be 0.5 volts into capacitance. Here the charge is 0.5 volt, 1 volt into capacitance. So, as the drop in this along the channel increases, the charge will vary from this end to this end. It will more charge here corresponding to 1 volt, at the end it will be voltage available for creating the charge is less, so charge is less. So, that is what is shown here. So, as the current begins to increase, more charge here, less charge here, it looks as if you have a resistor whose area of cross section is changing. So, if the resistors were the same thing, okay, if it is of same area, rho L by A, when I increase the voltage, resistance is not, if resistance is not changing, current will be actually increasing. V is I into R. R is constant, if I increase V, I will increase. But in this case what happens is, because the area of cross section is decreasing, when the current begins to flow, the resistance increases. So, V is equal to I into R, but when you increase V, I increases, but R also increases. So, V by R is I. So, V increases, R also increases to some extent. So, I does not increase linearly. So, that is how the VI characteristic I does not increase linearly beyond a certain voltage. When increase VD, it will start deviating from linearity, and at a particular voltage, when it opens up, there is a fixed voltage across that. Let me not get into the theory of that. When this voltage, in this example where I have given, the threshold voltage, minimum voltage is 1 volt, and I apply 2 volts. So, if at this end 1 volt is available for creating the charge, but at this end, if this is 1 volt, the voltage available is actually 0 volt. So, charge will be 0 here. So, when this opens up here, beyond that point, the voltage drop across this channel is 1 volt, resistance is not changing after that, all that voltage that you apply goes into the junction. I quickly run through this thing, because there are a lot of physics involved in that. So, beyond that point, once this opens up, current saturates. So, this is the IV characteristics for the MOSFET. VGS equal to threshold voltage, small current, VGS equal to 2 volts, it saturates. Okay. When the drain voltage is equal to VGS minus V threshold, it begins to saturate. That is, the example is V threshold is 1 volt, if VGS is 2 volts, when VDS is equal to 1 volt, it will actually saturate. Okay. Now, if you do not want to go through more details, the current in this portion is related to this gate voltage by this relationship, square law. ID SAT is some constant which depends upon the dimensions of the MOSFET into VGS minus V threshold square. If VGS is 2 volts, if V threshold is 1 volt, it is 1 volt square into some constant, that is the current. So, current varies as square of the gate voltage. Now, what I have discussed is mainly N channel MOSFET. Okay. Just like the BJT, you can have N channel and NPN and PNP. Here you can have N channel and P channel. In the N channel, channel is made up of electrons, source and drain are electrons, current flow is from the drain to the source because the charges flow in this direction, gate voltage is positive, create electrons. In the P channel, so that is N channel. The symbol is this, you can even put it like this, gate, source, drain. It is shown broken, when you apply plus voltage, the switch is closed, path is there. This is one of the symbols that is usually used. You can see the arrow like P to N, the arrow channel is negative. So, the arrow is from the substrate to the channel. So, that is N channel. P channel, N plus is replaced by P plus. P plus meaning heavily doped P, lot of dopants. Drain is also P plus, and the substrate is instead of P type, it is N type silicon. And gate voltage here in the N channel you apply plus, here you make it negative. So, the charges are plus, that is the holes. Okay. So, the current flow is due to the injection of holes from here to here, and the current flow direction is same as the hole flow, it is like that. So, you can see the current direction is exactly opposite to that of N channel, this is a P channel. Gate voltage negative, drain voltage negative, so that plus to minus current flows. Symbol is exactly opposite. Substrate is N, channel is P, P to N is the arrow direction. Okay. Now, the transfer characteristics which you take, if I take for once the current is saturated, if I go in this direction, constant VDS if I take, you can see it is independent of drain voltage at this point. So, if I do that, this square law if I plot, up to threshold, when till VGS is V threshold, current is 0. Beyond that point only current starts flowing, that is shown here. ID versus gate voltage in the saturation region is up to threshold voltage. I put symbol N here to show that N channel current is practically negligible, then it increases as square law. P channel drain voltage is negative, I put it in this quadrant, but the current increases in this direction with the same square law, but you must have a minimum negative voltage which is equal to BTP, maybe half volt. Today they talk of 0.1 volts, 0.15 volts as the threshold voltage in the when you go to submicron devices. Okay. Now, before we go into more of the amplifiers, we will leave the device physics. Just one terminology for, because you keep hearing about this often, that is the CMOS. What is the CMOS? All the circuits, digital circuits are CMOS circuits. The basic building block for the CMOS is this. It has, this is the N channel MOSFET, this is the P channel MOSFET. Okay. You can think of it as two switches connected in series. This switch will be closed if this gate you apply plus voltage. N channel, if I apply plus voltage, the switch will be closed. P channel switch will be closed if I apply negative voltage with respect to source. Here you see connection is source, drain, current flow will be in that direction. Here the source is connected to supply, drain is like that. Current flow is from the drain, the source to the drain. Please remember here, current flow is from source to drain, here current flow is drain to source. You connect the two drains together in this fashion. So, I can have, if this is 0, how this works out is it's a digital circuit. If the input is 0, okay, this will be off. Input low, 0, this will be off, switch will be open. But if this is 0, because the source is positive, the gate is negative with respect to source, therefore, this switch is closed. So, if this switch is closed, this switch is open, bottom switch is open, this switch is closed, VDD is connected to this path to this output point. Since there is no current, this switch is open, there is no current flow. So, since this path is closed, switch is closed, VDD will appear here. So, what we say is, if this input is low, this switch will be off, this switch will be closed. So, V naught will be equal to VDD. Input low, output is high. Input is 0, output will be VDD. It is inverting the input. Okay. Now, if input is high, that is this is VDD, this is VDD, the voltage across this is 0, that will be off. And if this is VDD, in the digital circuit this will also be VDD plus high. The gate of this N channel MOSFET is high, positive, therefore, this switch will be closed. So, if this switch is closed, there is a path from here to here. So, this source is at ground, there is a path here, but there is no current flow through the circuit because this is open. This is open because this is 0, but this is plus. So, okay, I am sorry, this is 1, this is 1, this is high, this is the voltage across this is 0. The voltage across the P channel MOSFET is 0, the voltage across this is high, therefore, this switch is closed, this switch is open. So, supply voltage does not reach because that is open, but this point is connected to this. This is ground, so that is 0. So, when the input is high, this is low. So, you can see this is the basic building block, making use of this. You can make NAND gates, AND gates, all sorts of things you can make using OR gates, NOR gates, you can make using this type of gate. Basic building block is this. So, this is called complementary MOS circuit. Complementary because this is N channel, this is P channel, complementary exactly identical or slight difference. So, they are complementing each other because they are one is N channel, one is P channel. Okay. Now, let us switch gears and leave this topic of device physics and operation of the devices, go into amplifiers. This will be much simpler. Basically, you will be able to understand this with minimum understanding of the devices. Now, why do you need an amplifier? Whenever you have transducers, for example, pressure sensor or acceleration sensor, etc., those transducers give output voltages which are in microvolt range or millivolt range and possess very low energy. If you want to make use of that for some actuation, or if you want to make use of them to do some work in the external world, okay, you must raise their power level. You must have signal conditioning circuit. Signal processing is easy if the signal is made large in the range of volts. So, what you need to do is, whatever signal comes in from the transducers, you need to amplify it. So, this is a block diagram of an amplifier which has 2 input terminals and 2 output terminals. These bottom may be common. I have not shown them common. This may be ground, this also will be ground. So, here within certain range of input voltages, the characteristics of this amplifier will be linear. Output will be proportional to the input, or output current will be proportional to the input current. Okay. So, within that linear region of operation, you will have the voltage gain AV is V naught. This block that I am showing is a resistor or a load. Okay. It can be a motor which you want to run, that is represented by means of a resistor here. So, load. So, the voltage here is V naught, the input voltage is V in, V naught by V in is actually the voltage gain AV. Now, if it is linear, the slope of that delta V naught by delta V in is exactly equal to V naught by V in. If it is nonlinear, over a small range of that curve, you can approximate it to be linear, and you can still call delta V naught by delta V in around that voltage to be the voltage gain. So, the voltage gain is V naught by V in. Similarly, you can talk of current gain I naught, current at the output divided by current at the input, that is the current gain. Okay. Now, power gain V naught output voltage into output current, that is the power, divided by input voltage into input current, that is input power. So, voltage gain into current gain is the power gain. So, what we are telling is, if I have certain signal with certain power input, you will get for the same signal higher power output. Okay. This looks like against the law of thermodynamics. If I give input power, how can the power output come more? The output power has come from the internal circuit. There will be DC power supply within this amplifier. This may be AC signal here, AC signal coming out. I will have DC bias supply which is used within this amplifier. You can see whenever you use an op amp, a circuit, you have to switch on the power supply, and power supply is supplied to this amplifier. The source of power is the DC power supply. So, if you have amplified this signal from here to here, if the power of the input signal has got amplified and you have got more power output, that extra power has come from this DC power supply. So, supply comes from the DC power supply. So, that is the purpose of the power supply. Okay. Now, many times these gains may be very large, 10 to the power of 5, 10 to the power of 6 of that order. So, in order to simplify that, in many places you will see that these gains are expressed in logarithmic gain. as decibels. So, if I want to see, you saw the power gain is AP is output power P naught divided by input power P in. Now, I can express it as 10 log power gain, 10 log to the base 10 P naught by P in, output power by input power. The way of defining, that is all, decibels. So, do not get perturbed if someone comes and tells you I have 60 dB power gain, means this is 60. That means this is 10 is there and this is logarithm term is 6. Okay, that is P naught by P 1 is equal to 10 to the power of 6. 10 to the power of 6 to the base log 10, if you take it is 6. So, 60 dB means 10 log 10 to the power of 6. So, gain is 10 to the power of 6, you call it as 60 dB. There is a power gain. Now, power is proportional to V squared. So, I can put this as V squared by V in. When you say voltage gain in dB, the same symbol you use 10 log V square by V in square. So, logarithm of square you can take it into this side 20 log V naught by V in. Okay. So, voltage gain in dB is 20 log V naught by V in. So, here you can see if I have 10 to the power of 3 as voltage gain, logarithm of 10 to the power of 3 is 3, the gain in decibel it is 60 dB voltage gain. Same way current gain, power is proportional to I squared R. So, I squared by I in squared is the log you take, same definition you use, replace P naught by I squared I in squared. So, you get 20 log I naught by I in. So, again it is logarithmic of that. If this is ratio is 10, I naught by I in, log 10 is 1, the in dB it is 20. Okay. And if I naught is less than I in, okay, this will become negative. The term will become negative. Logarithm of 1/10 is minus 1. So, minus 20 dB it will be if it is 1/10. Okay. Now, there are other terminals which one comes across. Input output resistance. In an amplifier, particularly when you talk of op amps, you will talk of input resistance, output resistance. Input resistance is a measure of the current drawn by the amplifier. Supposing I have certain, I have marked this a V in plus minus, it can be AC or DC. Okay. So, if I have a V in here, if a current drawn is I in, then you say it looks as if there is a resistor put which is equal to R. It can be resistance or impedance. So, to simplify we talk of resistance. So, V in divided by the input current will be the resistance, input resistance. Now, in other words, if I know what is the input resistance of the amplifier, I will be able to tell how much is the current for a given voltage. And if I know how much is the current, I may be able to tell how much is the current here. For example, in the transistor case, if I know the emitter current, I know how much is the collector current. It is almost equal to the same thing, alpha times I e, which is 0.999. So, okay. So, if I know the input signal from the amplifier configuration, you can tell, you can determine the input resistance. Okay, then you can find out input current and you can find the output current. And if you know the output current, you can find out what is the voltage at the output is. Output current into resistance with the output, this resistance gives me the output voltage. Then you know the voltage gain. This is just some minimal understanding. Now, so what you have done here is you have replaced the entire thing here by means of a resistor to find the input current. Same way you can, looking from this side, you can replace the whole thing by means of a voltage source in series with the resistance. I am sure all of you have studied what is known as Thevenin's theorem. You can replace the network by means of a voltage source and a resistance, and that resistance is the internal resistance seen from here, that is the output resistance. Okay. So, the input resistance is much more useful than the output resistance, except in some cases. Okay. So, this is resistance looking from this side. So, you have the voltage source in series with the resistance. If this resistance is large compared to the output resistance, entire voltage appears across the load. If the output resistance is large and this resistance is small, then out of the voltage that I have amplified, very little will appear across the load. It is like a battery. If you take a battery, when it is new, you put a voltmeter, you will see the voltage. Okay. Cell voltage you will see 0.5 volts or whatever it is. Now, when the battery gets old, you put a voltmeter, you see the same voltage almost 0.5 volts. Okay. So, let me start once again. When it is new, you put a meter, you get the same voltage 0.5 volts. If you connect a load resistor, small, okay, whatever be the resistance you connect, the voltage across the load will be the same as the voltage that battery supplied, because the output resistance of that battery is small, 1 ohm or half ohm. So, if I put 10 ohms, half ohm and 10 ohm in series, entire voltage goes to 10 ohm. But if you use a rundown battery, okay, when you put a voltmeter across the battery, it will show 0.5 volts. But when you put a resistor across that, okay, when you put the resistor across that battery, the voltage will drop. It will not be 0.5 volts. It will not be able to drive the current, because voltage has dropped. Why is it so? Because the output resistance of that battery has gone up. So, when the battery is run down, if you no load, it may show you, oh, voltage is there 0.5 volts, whatever voltage is required. But when you connect a load, the voltage will fall down, because it has developed an internal resistance. That is the output resistance, the internal resistance of the battery. Here in this case, the internal resistance of the amplifier, which is characteristics of that amplifier. So, that will decide how much load you can put here. If that is very small, best, it will, whatever voltage is available will be available across the load. Okay. Now, I have already mentioned about this thing, the DC power supplies for amplifier, okay, are used, required to set up the operating point, so that the AC signal can be superimposed as shown here. See, for example, this is amplifier diagram I have shown. You have the DC and the AC. Now, the amplifier characteristic is like this. Okay. If I have a bias like this, when I do not have the signal, I already applied VDC here, input versus output, this is the operating point. Now, I superimpose AC signal on that, it will go around that here. So, correspondingly the output will be varying around that like this. This is a crooked signal, okay, it is not a good sine wave. So, it will go up like this, input was varying around this like this. Input varies around x axis around this VDC, output will vary around DC V naught in that fashion. So, now you can see that you can superimpose this, you can analyze it DC and AC separately, you can separate out DC and AC. If you put a capacitor, the DC will be blocked, you can get only the signal. If I have signal here, I can get only signal here, removing the DC by coupling a capacitor here and taking the voltage at the output. Okay. Now, DC power supply provides the power delivered to the load, that I have already mentioned that. Okay, this is the source of power, if I have power amplification here. Okay, now, to give a good example of the amplifier, I think this is the last thing that I have discussed today about this thing, because op amp I will start in the next presentation. This is an amplifier circuit. This makes everything clear. This is the common base circuit. I have the DC which biases in the forward bias direction, and I have superimposed AC signal which drives a current IE through that, and okay, that is the input voltage V in that comes across this point at the emitter, between the emitter and the ground, input AC signal that is coming here. That signal is whatever current comes through that into the resistance seen here. The resistance seen is for the AC quantity, incremental quantity. Okay. So, for signal, we will see how much is the resistance here. Let me call it as R E resistance to that AC signal R E. So, if I E is flowing through that, I E times R E, see I have made it everything simple linearized. I E, see there are DC signal, AC signal. We are interested in the AC signal. I E times R E is the AC voltage across that, but I E is the AC current, signal current. It need not be sine wave, signal current. And signal current is I E. What will be the signal current here? PNP transistor, if signal is in this direction, I E is in this direction, I C will be in that direction. You see here also corresponding to DC current, I have DC current capital, corresponding to AC current, I have AC current. This AC current only I am dealing now, you can superimpose and talk of them separately, I am talking of AC only. This small I C is related to I E by the current gain alpha. I C is alpha times I E. Okay. I C is I E times I E, and the drop across this resistance is AC drop is I C into R L. I C is alpha times I E into R L. I hope it is clear. So, V naught is the AC voltage. This you can remove by putting a capacitor, you can measure only the AC signal. So, I am considering what is the drop across this resistor R is, that is I C signal current into R L, signal current is alpha times I E. So, alpha times I E into R L is the voltage output V naught, AC voltage small, and input voltage is AC current into input resistance I E times R E. Now, you can see I get cancelled and alpha times R L by R E is the voltage gain, and alpha is almost equal to 1. Therefore, voltage gain is R L by R E. Now, let me see R L is 1 K. What will be the order of R E? R E, this is a forward bias junction, the resistance will be very, very small, it will be of the order of 25 ohms. If this is 1000 ohms, 1 K, and if this R E is 25 ohms, the voltage gain is 1000 by 25, that is 40. So, you will get a voltage gain of 40, but current gain was actually alpha was just nothing there, less than 1. So, alpha is less than 1 or close to 1, voltage gain is 40. What is the power gain? Current power gain is current gain into power gain. Current gain is just almost 1, voltage gain is 40, power gain is 40. So, you have got the power gain of 40. The power has come from these batteries. Okay. So, now just to take a look at this. So, that is the idea of the amplifier. Now, just to take a look at this incremental resistance, what is that? Just see this input characteristics. Input characteristics, i.e. DC current versus DC voltage across the diode is like that. Now, I have a small signal superimposed, this is the DC bias point, small signal I have sine wave superimposed on that. Okay. I can treat this as a linear region. So, this I E there will be related to this input. If I treat this as a linear region, just simplify it like this, I E is I naught e to the power V by V T, that is the diode equation. What I want to find out is how much is delta I E, and for a delta V B E, I differentiate that will be 1 by V T. See, differentiate this V B E, this is 1 by R E, current divided by voltage is 1 by resistance, incremental resistance, and this quantity is delta I E by delta V B E, V B or V B E is 1 by V T into the same quantity, that is I E. So, R E is V T by I E. What is V T? V T I have already mentioned last time that it is about 25 millivolts, that is K T by Q. K is Boltzmann constant, T is the temperature, room temperature. At room temperature, this thermal voltage K T or V T is 25 millivolts. So, if the current is 1 milliampere, 25 millivolts by 1 milliampere, 25 ohms. That is why I said this R E is 25 ohms in this case. So, 25 ohms, this 1 ohm we have put there like that. Okay. Now, the last one I want to see how much I can discuss. Here we have seen that you have some sinusoidal wave, this signal sinusoidal there. How much voltage you can apply at the input, or how much can be the maximum output voltage? Okay. These are all the common base characteristics, 1 milliampere, 2 milliampere, 3 milliampere, 4 milliampere. I am considering a case where this V c is 4 volts. Okay. If this V c is 4 volts and if the resistance is R L, if I plot this is output characteristics of the transistor, B B C versus I C, common base characteristics are this. For different I E, I get this current. Okay. So, 1 milliampere emitter current, 1 milliampere collector current, 2, 2, 2, 2, 4, 4, because alpha is almost equal to 1. Now, if this supply voltage is 4 volts and if I am talking of 2 milliampere current, I have adjusted this DC bias here. So, that DC current is 1 milliampere, collector current is 1 milliampere. What is the drop across this R L? If R L is 1 K, if there is 2 milliampere current, what will be a drop? 1 K into 2 milliampere, that is 2 volts plus minus 2 volts. This is 4 volts. So, there is a, out of 4 volts, 2 volts has gone into that, B B C will be only 2 volts. That is the point that I put here. So, your voltage, this is the load line, let us not worry about that. At 2 milliampere current, collector current, the resistance also has got 2 milliampere, that is the meaning of that. The voltage drop across this VBC is 2 volts. Okay. Now, I superimpose a signal I E here like this, I E varies around that. Suppose this I E varies from 2 milliampere to 4 milliamperes, it goes up. What will happen? If I E goes up, collector current also goes up. If it is 4 milliampere, drop across that is actually 4 volts. So, net drop across that will be 0. So, you are actually at this point. The signal cannot go beyond that point. In fact, it will get clipped. That is called saturation. I will get back to this once again maybe in my next lecture, because this needs bit attention. Similarly, the maximum limit up to which the swing can be there, output voltage will be, one is the 0, other one is the power supply voltage. So, the signal will get clipped or saturated if the output reaches, the signal goes from maximum of 2 volts, minimum of 2 volts in this example. So, what is the upper limit? Upper limit is supply voltage, lower limit is that 0 bias voltage. So, with that I think I will conclude. I will come back to this and take on the op amps in my next lecture. Thank you.